Light traps are an excellent tool for the collection of flying insects. They are fairly easy to use and are able to exploit the many insects who are attracted to light. Moths comprise a large amount of the easily accessible prey from the trap. There is no verified explanation for moths' attraction to light, but a widely accepted theory is their relationship to the moon. This theory states that moths migrate using the moon and the stars as navigational aids. The placement of a closer light source causes subtended angles of the light to the insect's eye. The angles alter so rapidly that the moth has to fly in a spiral to reduce angular change, resulting in an insect flying into the net. Another explanation is that moths become truly trapped by light because it induces sensory overload that disorients and sends them into a stunned state. In order to escape, they circle over and over until they come to a rest. Generally, once a moth is attracted to the light, they very rarely ever leave and proceed to hang around the light indefinitely. It is a well-accepted but not a well-understood phenomenon that insects are attracted to light, and light traps are able to capitalize on this.
In general, the best places to place light traps are in open fields, yards, or trails. According to the moon navigation theory, the best time to collect is during the new moon because there's the smallest amount of light competition. Moths prefer warm, windless, humid, and cloudy nights, so it's best to set up traps when temperature is around the 40s or above. Any type of incandescent bulb can be used, but mercury vapor bulbs that emit UV light work well due to emitting a broader spectrum of light which targets a larger range of insects. Light traps are fairly easy and inexpensive to use. All you need are laundry pins, an extension cord, a large mercury bulb, hanging frame, which we kind of don't have, but this is the idea, a white sheet, and an electricity source, such as an outlet anywhere nearby, goggles that protect against UV light, nice, tonic water, which helps you determine whether your glasses or goggles are properly blocking the UV light, rope, which will be able to tie down the frame when it's really windy, and then weights, which do the same thing. We don't really have the specific weights, but anything heavy, such as a jug of water, etc., will work. An aspirator to collect the smaller insects, and a kill jar, forceps, and a Ziploc container to collect the multitude of insects you will trap. Now we will begin setting up the light trap. First, you need to set up a device for holding the sheet. We don't have a frame, so we'll use a whiteboard to show how the setup would work. The white sheets are used to reflect light and provide a landing platform for the insects. You just put clothespins on the end to keep the sheet stable and taut. So normally we would use more clothespins to have it be as taut as possible, but they won't fit on the whiteboard. And An optional but effective way to use this trap on a windy day is to also tie a string to the top of the frame and hold the other end under a heavy object behind it for stability in order to prevent the frame from falling forward onto the light bulb. Many of us found this necessary on the first field trip because of how windy it was. Next, you need to set up the tripod and attach the light bulb. You need to make sure there's a power source nearby or that you have a long enough extension cord. In the event of rain, which many people experience on the second field trip, a good way to protect the light bulb is to use a cover in which you screw the light bulb into the bottom of this to protect it from the rain. Apparently these light bulbs will crack as soon as they're touched by water. Lastly, just turn on your light bulb and the trap is set up. Also wear your goggles for UV protection. Ta-da! The light trap is set up. Light traps are a very useful and efficient method of trapping because they exploit insects' unique relation to light, and they provide a good sample of what kind of insects are active at different times in the night and information about relative abundance and species composition within the area.
Reporting live from the field, it's 3 a.m. in Slocum, Washington, and we are in front of the light trap. The temperature is in the upper 50s and the wind has subsided. We have been recording the numbers of various insect orders present, counted for 5 minutes each hour. Here we collected our data. Teams of 2 rotated shifts at each hour from 9 p.m. to 5 a.m. over the course of 2 nights. Unlike the first night, the second night was warmer with less wind, so the numbers seen were greater. Moths of eastern Washington that are active during the month of May, which is when our field trip occurred, include the ornate tiger moth, the Ceanothus silk moth, the wild cherry sphinx moth, and Synaxis and plume moths, all of which were collected at our light trap. Day 1 collection from the light trap was difficult as conditions were colder than Day 2 and extremely windy. The light trap fell over on many occasions, leading to a loss of specimens that otherwise would have stayed on the sheet. In such a way, the count of individuals of each order is lower for Day 1. The data for Day 1, the night of May 15th to the morning of the 16th, shows a slow decline of Diptera fly numbers from 9:55 p.m. on throughout the night, except for a peak which occurs at 2:55 to 3 a.m. Orthoptera, mostly comprised of grasshopper, numbers showed little variation throughout the course of the night, except for around 2:55 to 3 a.m. when none were present. Finally, Lepidoptera numbers were the lowest throughout the night, with exception of 1:55 to 2 a.m., when a peak of 13 individuals was observed. We theorized that the trend of variation at 2:55 to 3 a.m. could be due to an event of the trap blowing over, in which case the flying species would be faster to recolonize the sheet. Day 2, the night of May 16th to the morning of the 17th, conditions were more favorable, with no wind and temperature in the upper 50s. As a result, many more individuals of each order were observed at the light trap. Diptera numbers fluctuated greatly, increasing from 9:55 to 1 a.m., then falling dramatically between 1 a.m. and 2:55 a.m., between which, unfortunately, no data was collected, after which the numbers increased again. The opposite trend was observed in Orthoptera numbers, with a decrease between 9:55 to 1 a.m., and then a dramatic increase between 1 a.m. and 2:55 a.m., after which the numbers dropped again. Again, Lepidoptera numbers were the lowest, dropping from 10:55 to 11:55 p.m., but then increasing slowly until sampling ceased at 4 a.m. In all, Diptera yielded the highest number of individuals, with 184 observed over the 2 nights. Orthoptera was second highest with 110 individuals, and Lepidoptera was the lowest with only 86 individuals observed.